Alright, so in this video, we'll be looking at the mechanism for benzene sulfonation. That is the sulfonation of our benzene. So looking at an overview of what this reaction looked like, we can see that we start off with a benzene molecule, right? And we have 3 double bonds in here. And this benzene is going to be reacted with H2SO4, that is sulfuric acid. And this reaction is then going to yield this molecule over here. Again, still with our 3 double bonds in our benzene, but here we will now have an SO3H group as opposed to the hydrogen that we normally see in our benzene. And it's important to know that this is a reversible reaction. So we are able to go back from this molecule here, which is known as benzene sulfonic acid, both benzene sulfonic acid. So we can go from our benzene sulfonic acid back to our benzene. And how can we do this? Well, if we take our benzene sulfonic acid and we react it with water under high temperature conditions, we'll be able to reform our original benzene molecule here. Again, now with our hydrogen group here instead of our SO3H. So now, let's look at the actual mechanism. How is this reaction occurring? Well, in order for us to, undergo this reaction, we're going to need an electrophile. So what is the electrophile in this reaction? Well, we're going to form or generate our electrophile using our sulfuric acid. So we can see that by reacting 2 sulfuric acid molecules with each other, we're able to generate a pretty good electrophile. So if we have 1 sulfuric acid molecule here, which we can then react with the other, we can see that one of these sulfuric acid molecules is going to serve as a source of protons for the other. So we're able to protonate one of our sulfuric acid molecules from the other. So we can use the double bond, or we can see the electrons here, the lone pair on this oxygen is going to go on to attack this hydrogen, which causes this bond to break, allowing us to protonate our OH. So what we're doing is effectively turning that hydroxyl group from a bad leaving group into one that is good. So instead of our OH, we now have an OH2 with our still 1 lone pair and now a plus charge. And remember, our sulfur here is still going to retain these 2 oxygens that are bonded using, pi bonds here. So what we'll see now happen here is our oxygen has its 2 lone pairs, which it can use to attack here, which then breaks off this water molecule effectively, giving us now a molecule that looks something like this. So we have our sulfur bonded to 2 oxygens with a double bond, and we'll then have bonded to an OH plus. So this is going to be our electrophile for this reaction. So this is our electrophile. And so remember, when we were doing this, we were basically just expelling a water molecule. All right, now that we have our electrophile, let's look at how this is going to react with our benzene. So we start off with our benzene here, which has its 3 double bonds. And let's draw out our hydrogens here, at least 2 of them. So then we have our electrophile also, right, that we generated in the last step. So let's also include that. So this is our electrophile. So what happens now? Well, in this reaction, our benzene here is going to attack the sulfur. So this pi bond, or this double bond, is going to go and attack our sulfur. So if we do that, that's going to cause these electrons, or this bond, to break and collapse on our oxygen here. Now what we see forming is our intermediate molecule is something that looks like this. We no longer have our 3 double bonds. We now only have 2, and in place we have our hydrogen, which was we had before, and in place we have our benzene bonded to our sulfur, which still has its 2 oxygens, and now just an OH, as we saw that these electrons had collapsed onto our oxygen that initially had a positive charge. So now we just have a neutral hydroxyl group. And we still have our other hydrogen here, but as we saw, we lost a pi bond. And so this carbon here is now going to have a plus charge. So what we're going to now have to do is we react this intermediate with a base. We react this intermediate with a base. So now what is going to be that base? Well, there are a couple of options, right? Our base could either be water. We could also just use our H2SO4 minus, which is our deprotonated, our HSO4, right? This was our deprotonated sulfuric acid earlier when we were forming our electrophile, HSO4 minus. This could also serve as a base. Or simply, depending on whatever solvent we're using, if we have a solvent that would serve as a good base, we could also use that. So any one of these could be used as a base in this next step. So we'll instead just use a generic base for all purposes. So what we'll see is this base is going to go and attack this hydrogen, causing these electrons to collapse. And what we can see then forming is we have now reformed our benzene with its 3 bonds, and we have an SO3H group in place. And now we've lost this plus on this carbon as we have reformed the double bond. And this is our benzene sulfonic acid. Benzene sulfonic acid. So that's it for this reaction. Just as a quick recap, we're going to be starting off with this electrophile which we generated from our sulfuric acid, and our benzene ring. Our benzene is going to attach the sulfur, which is going to then cause us to form this intermediate. This intermediate, which, let me mention, is very unstable. It's very unstable. And following the formation of this unstable intermediate, we are going to have an attack done by a base. So our base is going to go on and attack our hydrogen, causing the electrons in this bond to collapse on our carbocation here, reforming our double bond. And this product, this benzene sulfonic acid, is going to be very stable. So what you'll need to remember in chemistry, right, is that if something is unstable, it is going to be unhappy, right? And if it's unhappy, it's going to be reactive. It's going to want to react quickly to get out of this unhappy state to a more stable or happy state. So this stable benzene sulfonic acid is very happy and thus unreactive. So what we'll see happening here is, I did mention that this is a reversible reaction. So how is it reversible then? Well, that goes back to simply the concentrations of our different products. So if we have a solution that is very high in benzene sulfonic acid versus one that is high in benzene, we can shift the direction in which this reaction proceeds as per Le Chatelier's principle. But what's important to understand is that this intermediate is very unstable, and that's because our benzene is an aromatic molecule. It is aromatic, and that is a very stable condition. And so in this case here, when we break that double bond, we have lost the aromaticity of our benzene, and so it is going to want to return to that stable aromatic state, which is possible in this benzene sulfonic acid. And so we can see that this is going to occur very quickly. So the slow step of this reaction is going to be the formation of this intermediate, because it's very energetically demanding, since this is an unfavorable state to be in. But then going from this intermediate to our product, the benzene sulfonic acid, is going to occur very quickly. So this is going to be a fast step, and this is going to be slow. All right, so hopefully that is making sense. This is another example of an electrophilic aromatic substitution reaction. That is an EAS reaction. So there are going to be a couple of these that we will be going over in the coming videos, but this is an example of an EAS, electrophilic aromatic substitution. So that brings us to the end of this video. I hope it was useful. If so, please show your support by liking and subscribing. Leave in the comments any questions or suggestions for future videos, and I will see you in the next one.